Imagine there's an invisible field everywhere in the universe, and it's responsible for our existence. Does that sound familiar? It's not religion, it's science. If there's an invisible field, you can't just talk about it. You have to find it.
Nu ska vi ut i rymden igen. Professor Lawrence Krauss har ju gjort sig känd som en stridbar och provokativ vetenskapsförsvarare. You don't know what I'm saying, that's very funny actually. En kosmologins gossen Ruda. Han har tillsammans med Richard Dawkins gjort en underhållande och ganska kaxig film som heter The Unbelievers, som jag tror har sänds på svensk tv också. Så här skriver han i inledningen på sin nya bok, Den största berättelsen. I begynnelsen blev ljuset till, men inte nog med det. Det blev gravitationen också. Och sen brakade helvetet lös. Och så fortsätter han. Så börjar berättelsen om det mänskliga intellektets hittills största äventyr. Berättelsen handlar om vetenskapens strävan att uppenbara verkligheten bakom världen som vi upplever med våra sinnen. Ett företag som har krävt att själva höjden av mänsklig skaparkraft och intellektuellt mod har mobiliserats. Och det i en global omfattning som saknar motstycke. Och det hade varit omöjligt om inte viljan funnits att bortse från alla sorters övertygelser, förutfattade meningar och dogmer, vetenskapliga såväl som andra. I'm quoting from your book. So ladies and gentlemen, please welcome the starman of cosmology, the Major Tom in David Bowie's Space Oddity, Professor Lawrence Krauss.
Wow. Thank you. Thank you. Thank you, Kristen. Thank you. Thank you. I'm very happy to be here. I'm not so happy to talk about what I'm going to talk about after you've been listening to deep ideas for an hour and a half. But I am happy that Richard read from his book, partly because I love listening to Richard read, but because in a way it introduces something that I want to get to, which is the subject of the talk. And it's really from this quote, which is one of my favorite quotes from another naturalist. And it's a book called The Peregrine. A friend of mine, a filmmaker named Werner Herzog, introduced me to it. It's the hardest thing to see is what is really there. This book, by the way, is about a peregrine, in case you're wondering. But what Richard was talking about was the illusion that we have. And the first person to really point out that the world we see is an illusion in that sense was Charles Darwin. That the illusion of a static world with everything created the way it is was in fact an illusion because we live short lives in a long universe. And what I want to talk about in the next hour or so is another illusion, and one that probably in my mind is one of the most amazing illusions of reality, because that's what science does. It peels back the illusion of reality. And so the example I want to use is this, which happily you recognize here. In Phoenix, where I teach, I showed this and people didn't know what these were. So these are ice crystals on a window, and I want you to imagine the illusion you'd have if you lived on one of these ice crystals. If your whole civilization evolved on one of these crystals, what would happen? Well, there'd be a very special direction. That direction, the laws of physics would be different in that direction than this direction. And physicists would come up with those laws and explain that the laws were different in this direction, that direction. Theologians would explain why that direction was meant by God. And then there'd be wars over whether it was that direction or that direction. That was the most important one. And that because it would take on a significance. Now, what I want to tell you about is, in fact, something that science has shown us in many ways, but most particularly with the most recent developments in the last 40 years. And that is that the universe that seems designed for us, with laws of physics that seem designed for us to be able to live in it, is an illusion. That at a very fundamental level, the laws are quite different. In fact, they wouldn't even allow for our existence. If there wasn't an accident very similar to this accident, we wouldn't be here. So there's no sense in which the universe is designed for us. There's no sense in which it's made for us. And I find that remarkable. But the discovery of that is a long story, and that's what my last book is about. So I want to pick it up near the end with this guy here, who you do recognize, Richard Feynman, who won a Nobel Prize and was here a while ago, and was going to wear it around he was going to put a hole in it and wear it as a medal, but someone talked him out of that. But Feynman came along at a point where we had learned, at that point, most of the physics that's really relevant for understanding our lives, almost all of it, in fact. And in fact, maybe we'll get to the fact that a theory of everything is probably a theory of very little in the end. But so we had general relativity, special relativity, electromagnetism. All of that had been described very well. Then quantum mechanics came along and changed everything and screwed everything up. And Feynman was one of the people who came up with a quantum theory of electromagnetism, and he did it pictorially. This is the way we understand the electric attraction or repulsion of two charges. We have an electron, and it repels another electron. The way we think about it in quantum mechanics, as Feynman told us, and this is called a Feynman diagram, is the electron emits a particle of light, because waves are also particles. Even the waves that Janet talked about are particles. They're made of particles called gravitons. The particles of light are called photons, that the electron emits a photon, and then that photon is absorbed by this electron, which gets repelled. It recoils. That sounds very nice, but it's impossible. It can't happen in a sensible world, because an electron can't emit a photon if it's just sitting there. Because if the electron's sitting there and it emits a photon which carries away energy, where did that energy come from? It's classically impossible. It's not allowed. But the quantum world is just like Washington, D.C. and the White House. Whereas if you can't see it, anything goes. Okay? And it's true, unfortunately, nowadays. And actually, it's even worse, because now if you can see it, anything goes. Apparently, still, it doesn't. But anyway, so this can't happen except for a law of quantum mechanics, the Heisenberg uncertainty principle, which tells us if we measure a system for a very short time, we cannot know the energy of that system exactly. It's not a property of your measuring apparatus. It's a property of the universe. And that means if this photon carries a small enough amount of energy, then you can't know it exists. And if it disappears in a time scale that's so short enough that you can't measure the energy it carries, then it's fine. It's like embezzlement, exactly, if you think about it. Embezzlement, when you take money out of a bank, if you work for a bank, and you go to the horse races, and you bet it that night, and as long as you make money and you return it in the morning before anything happens, it's fine. And this is the same thing. The photon can carry energy as long as you can't see it, which is why we call it a virtual photon, because it isn't really there because you can't see it. But that virtual photon carries energy and causes that electron to be repelled. And that is the way we understand electromagnetism. That crazy theory called quantum electrodynamics, which did win a Nobel Prize, is the best theory in nature. There is no theory that compares with it. You can predict from this theory to 13 decimal places any phenomena you can observe, and we can measure it to that accuracy. There's nowhere else in science where you can make that kind of prediction. So this is as good as it gets. And when Feynman and others produced quantum electrodynamics, it was basically all we need to describe essentially everything we measure in everyday life. Great. But then nature came along once again and screwed it up. A phenomenon exists, which I learned in high school, which surprised me. The neutron is radioactive. I learned it from a wonderful physicist named Tommy Gold, who I was listening to lecture. The neutron is radioactive. Now, that should surprise you, because you're made of neutrons. There are more neutrons in your body than there are protons. Many more. If I held a neutron up here, it would live about 10 minutes. Many of you, especially, will notice in your rear ends that you've been here a lot longer than 10 minutes. And you're still here. Some of you may wish your neutrons would decay, but right now. But they haven't. And that's really strange, because a free neutron decay in 10 minutes. That neutron decay was a phenomenon that was very strange because it meant there had to be something new in nature. A neutron decays into 3 particles, a proton, and this is a fancy way of writing an electron, and another really neat particle called a neutrino, which is my favorite particle, but I won't go into. But the neutron decays into these things in 10 minutes. But there's a remarkable coincidence in nature, that the neutron and the proton weigh almost exactly the same amount. The neutron has barely enough energy to decay into these particles, because its mass has to be bigger than the sum of the masses of these 3 particles. Great. Now, I drop a neutron in a nucleus. What happens? It gets bound. What does it mean to get bound? Well, you know what it means to get bound, some of you. But what it really means is you lose energy. If I jump into the audience, it would take energy to get back up on stage. So the neutron loses energy when it gets bound in a nucleus. Now, Einstein told us E equals mc squared. So it loses energy, and therefore it gets lighter. And when it's in a nucleus, it's too light to decay into a proton, neutron, electron, and neutrino. It's just that simple, amazing coincidence that the neutron and the proton have almost exactly the same mass. That means when you put a neutron in a nucleus in your body, it's stable, and you can hear this lecture. Okay? A miracle. A coincidence, as we call it in physics. Now, but this cannot be explained by electromagnetism or gravity or anything else. So there's a new force, and the first person trying to explain that force was another hero of mine, Enrico Fermi, who was the last great physicist who was equally adept at experiment and theory. And he came up with a theory, a tentative theory of how that would work, and he submitted it to the journal Nature, and they rejected it. And he got fed up and said, I'm not doing theory anymore, I'm going to do experiments, which was very good for him because he went and did an experiment right after that, and he won the Nobel Prize for that experiment, so it was good for him. But his theory was built on doing what physics does. Physics is like Hollywood. If it works, copy it. Okay? And keep copying it until it doesn't work anymore. That's the simple rule. That's why physics isn't complex, like Richard talked about. It's simple because we just keep using the same ideas over and over again. So this is the best theory we have in nature. So the idea was to make a theory that looks like that. And we can draw a picture. It's a little more complicated. A neutron decays into a proton, and then there's an electron and a neutrino come out. And if this interaction happens by the exchange of this particle called a photon, this one can happen by the exchange of a new particle. It's called a W particle. But the weak force, the force that produces neutron decay, happens inside a nucleus. But the electromagnetic force happens across the universe. The neutron stars that Jana talked about colliding are 130 million miles away, 130 million light years away, but we can see them, or at least we can see their effects, because light can travel across the universe. Electromagnetism can work across the universe. This works across the nucleus. So they can't be the same. Well, how can we understand this? Very simple. The photon has 0 mass. And 0 mass means this. Remember, the Heisenberg uncertainty principle tells you that you can violate energy conservation by a small amount if you measure a system for a short time. But because the photon has 0 mass, this can carry an arbitrarily small amount of energy. And if it can carry an arbitrarily small amount of energy, it can travel a very long time before it has to disappear. It can travel from here to Alpha Centauri. So the rule is in physics, if you want to have a long-range force like electromagnetism or gravity, the particle that conveys it must have 0 mass. This is a short-range force, so if this particle has a very big mass, you can understand that. If it has a very big mass, then it violates energy conservation by a huge amount when it's emitted, and it has to disappear very quickly. Great. We can understand this force being short-range and that one long-range if this has a very big mass. The problem is, it's garbage. It doesn't work. This theory produces infinities, which physicists hate. Mathematicians love them, but physicists hate them. This theory doesn't make sense. And this was so severe that in the 1960s, so many physicists just said, we have to give up relativity and quantum mechanics. It just won't work. They were willing to do that. And in fact, a number of them developed a theory called string theory as a way to try and get around this. And they were wrong then, too. But now a string theorist is operating my oh, there we go. Okay. Now, the thing I want to point out is another moral of this story, which I think is important when we're talking about science, as Richard just was talking about, for example, is that scientists are people. which is a secret, okay? But that means they're pig-headed, they have biases, they have ideologies, they make mistakes, they won't change their minds when it's supposed to be changed. That's okay, because the science overcomes that. And there were a whole group of people who were staring at this and doing exactly the wrong thing for 15 or 20 years when the right answer was staring them right in the face, because they were people. But the great thing about science is it eventually brought them around, and the science came from a very different area of science, superconductivity. In 1911, Kamerlingh Onnes discovered something remarkable. If you have mercury wire when it's very cold, if you cool it to 4 degrees above absolute zero, somewhat colder than Stockholm in the winter, then the resistance goes away. It disappears. Now, that may not sound crazy, but think about it. If you have a loop of wire and you connect a battery to it, and I cool it down below 4 degrees, so there's a current going in it, if I take the battery away, the current will still flow. Not for an hour, not for a day, not for a year, but forever. It'll never stop. It seems like magic. And it's a remarkable fact of physics, and it took about 50 years to try and understand that. But that held the key for this other area. Because now we can make high-temperature superconductors, and we can do little experiments in high school where if you put a high-temperature superconductor in dry ice and put a magnet near it, it floats. Why does it float? Because when it's a superconductor, magnetic fields can't go inside of a superconductor. So the magnetic field tries to permeate the superconductor. It dies off quickly. It gets repelled and basically causes that magnet to float. Now, what's this got to do with anything? Well, now I want you to imagine that you live inside this superconductor. What would the world look like to you, your myopic world? Well, for you, electromagnetism would be a short-range force, because magnetic fields and electric fields, when they try to go through your superconductor, die off very quickly. So for you, electromagnetism would be a short-range force, and if you derive quantum mechanics and relativity, you would then find out that the photon had a mass. And in a superconductor, the photon has a mass. That's what happens. The photon acts like a massive particle. And that finally dawned on people, in particular Mr. Higgs, that maybe this was the key. The key was like, imagine you're swimming through water very fast, but imagine I change the water and make it molasses and then ask you to swim. Well, first you say no, and then I say swim anyway, and then you swim and you feel much heavier. There's much more resistance. So imagine now that we live inside a cosmic superconductor. A cosmic superconductor in which some particles experience a resistance, in which some particles act like they're massive when really they have no mass at all. And if you can do that, you can draw a picture, at least, the Feynman diagrams. Here's the one I showed for electromagnetism. These are the same ones. There turns out there are 3 of them for the decay of a neutron, but it doesn't really matter. They look identical. If these particles that convey this force are absolutely massless, then the mathematics works out beautifully. But how can they be absolutely massless if the force is short range? If there's this invisible field everywhere in the universe, and these particles interact with it, if we live in a cosmic superconductor that these particles interact with and this one doesn't, they will act like they're massive. And this force will suddenly become short range. And these two very different forces in nature, they seem so different to us, and each one in their own way is important for our existence. They're as different can be. They're really the same thing. They're really different manifestations of the same thing. Whenever that happens in science, that's what progress is, certainly in physics. This would be true, and you could understand this theory unifying these two forces of nature, and it's a beautiful idea, except it sounds like religion. Right? Let me just remember what I just said. Imagine there's an invisible field everywhere in the universe, and it's responsible for our existence. Does that sound familiar? It's not religion, it's science. If there's an invisible field, you can't just talk about it. You have to find it. How can you find it? It's appropriate to talk about this in Sweden. Cosmic sadomasochism. You spank the vacuum. You spank it hard. Because in quantum mechanics, every field is associated with a particle. And it means if I dump enough energy at a single point in space, I might kick real particles out of empty space. If there's a Higgs field everywhere, I might kick out real particles. I'll call them Higgs particles. Where could I dump enough energy in a single point to create such things? you spend 40 years or so, almost as long as the LIGO experiment, building the most complex machine ever built. And the LIGO experiment is pretty complex. But the Large Hadron Collider in Geneva is this 26-kilometer long experiment that's, if you go to Geneva, you land at the airport, you look, you see beautiful farmland. Underneath it is this 26-kilometer long tunnel, and we accelerate protons at 99.999998% the speed of light in that direction, protons at 99.99998% the speed of light in that direction, thousands of times each second, and they collide at a few points, trying to dump enough energy into empty space to create these particles, the Higgs particle, if it exists. And amazingly, on July 4th, which is an important date in the United States, but not anywhere in the rest of the world, is now important everywhere in the world, because on July 4th, 2012, we reported 50 particles that walked like Higgses and quacked like Higgses, and therefore were probably Higgses. Since then, we've discovered all of the properties of the Higgs particle. We have discovered the Higgs particle. And we've discovered that this incredible picture, which is so weird, is true. We live in a universe in which we live in a cosmic superconductor. But that has not only changed our picture of the world, what I want to point out is that I think that's humanity at its best. The ability of humans to go where nature tells us, even if it's not pretty. The idea that what we see as a cosmic accident may not be pretty, but to me, it's what science does so beautifully. If you think of the Gothic cathedrals, they were built by thousands of artisans over centuries from many different countries. But the Large Hadron Collider is an example of how science brings us together. This isn't the collider. These are just detectors in the collider. Single detectors built by 10,000 physicists over 20 years from hundreds of countries, speaking dozens of languages and dozens of religions. Because unlike religion, science brings us together. And here, what they were trying to do, they weren't trying to build a better toaster or a faster car. They were just trying to answer the question, why are we here? How did we get here? What characteristics of the universe allowed us to be here? You go here, they're so huge you can't picture them. I have a better picture because I'm in it. But these things are amazing. And that we've been able to do it. And just to give one sample, there's a whole chapter in my book about the Large Hadron Collider because it's so amazing. But every second at the Large Hadron Collider, enough data is generated to fill more than 1,000 1-terabyte hard drives, more than the information in all the world's libraries. And while the vacuum that Janet talked about was 4 kilometers long, the vacuum in the Large Hadron Collider is 26 kilometers long. Again, more sparse than the vacuum outside the International Space Station. It's amazing that we have done that as a species just to answer these questions and just to be able to ask these questions. So I want to conclude with two things. First, what this really shows is our existence is an accident. It's identical to this picture. We are like people on this ice crystal. If this Higgs field had not frozen in the early history of the universe in the way it did, we wouldn't be here. The laws of physics would be different. Electromagnetism would be a short-range force, perhaps, and the weak force a long-range force. And all of the things that allow us to exist, all of the things that seem so fine-tuned about the universe are just a result of that accident. And it didn't have to be that way. Now, we may understand why it fell in that way, just like in principle we could understand why that ice crystal, due to the microscopic dust specks on that pane, formed that way. But the point is, it has no significance. That direction is no more significant than that direction. And you might imagine physicists on this ice crystal coming and finally figuring out that maybe there's nothing special about that direction, that in other places there could be other directions. And that would be at 3 in the morning. And then at 6 in the morning, the sun would rise and the crystals would melt and they'd be gone. That may also be our future. Richard was talking about the future and we were talking about comets, but forget that. In the future, the Higgs field could melt. And if it melts, everything we see in the universe, all the beautiful things that you saw in Janet's pictures, the galaxies, the stars, everything will disappear. Because nothing will have mass anymore. Now, don't worry about this, because it may happen. But, and in fact, it's really weird if you measure where the Higgs field is, the Higgs mass is precariously close to where this thing might melt. But even if it did, it would not be in millions of years or billions of years or billions of billions of billions of years, so you can keep your diamonds and the rest. But it may be the far future. The other illusion we have, which really evolution teaches us, and Richard was talking about it when he was questioned, is that the world is static. That somehow we're the pinnacle of evolution. We're not. We're a point in evolution. Somehow that the world is going to be the way it is, or the universe is going to be the way it is not the case. It will change. And to know how it's going to change, we keep having to ask questions. And that's how I want to end. This whole effort, which you've seen celebrated in different ways tonight, is based on asking questions about things that merely are related to our curiosity. And I am particularly worried of what's happening in the United States right now. But what happens in the United States, unfortunately, propagates throughout the rest of the world. And in my country, there's an idiot who's president. But worse, he's supported by a Congress of people who seem to be idiots. And it can happen anywhere. And they just put forward a budget early on that would cancel all support for the arts, humanities, public broadcasting. All of it would be zeroed out, saving $1.6 billion and spending instead $2 billion to build a wall with Mexico. Okay? That's what we have to fight against. Because asking these questions, what makes any country great, even that country, is not the walls we build, but the questions we ask. And so I want to close with a quote from the physicist who built the first large accelerator in the United States, Robert Wilson, who said, he testified before Congress about whether the accelerator he was building would aid in national defense. And this is what he said: "No, sir, I don't believe so. It has only to do with the respect with which we regard one another, the dignity of men." It was at a time before we said men and women. "Our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in the country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending." And that's what we should celebrate tonight. You are all kindred spirits, is the desire to keep asking questions no matter where it leads us. And only then will the greatest story ever told so far get better. Because there may be young people here today who will make the story better. And that's why the greatest story ever told so far, the story of science, is better than that other greatest story ever told so far, otherwise known as the Goat Herder's Guide to the Universe. Because it never changed. It was wrong then and it's wrong now. This one gets better, and we should all celebrate. Thank you very much.
Okay, we have limited time.
Yes.
It's getting late, so I think that we should get to the point. What was
good.
that?
What's the point?
No, the point is, what was that you said about string theory?
Oh, good. I said it because I knew I planted that question in your mind.
You did.
No, what I meant, and I think you'll agree with me here, based on what you said with Richard. Well, you'll have to agree with me because I'm right. But
I don't have to.
Yeah, no, I know. No, you said that you hated the idea of knowing of science knowing everything.
Absolutely.
And I think you will agree with me that that awful term that was applied to string theory of the theory of everything.
I agree.
I know. See, I told you you would.
That's an awful term.
No, because it's really understanding the relationship between gravity and quantum mechanics will help us understand not just what will happen in the center of black holes, but the beginning of the universe. And it's vital, of great interest if we want to understand our origins. But it's not everything. In fact, it's a theory of very little, if you wish, because the region where quantum mechanics and gravity is important, the two of them are important, happen twice in the universe, once at the center of black holes and once at the beginning. No matter what we learn about that, even if string theory were to give a description of quantum gravity that's accurate, even if it was a theory, it wouldn't describe how oatmeal boils or what, in fact, whether photosynthesis happens due to quantum mechanics. So science isn't going to end even if we understand the nature of the four forces. There's a tremendous amount of stuff we discover every day that's still going to require explanation. So it's never going to end. So that was my point.
Yeah, okay. But what about string theory? You still don't... string theory could still be true,
No, string theory is very
that could be the way to unify quantum mechanics and gravity,
No, string theory is the best game in town at this point. But
it could be that so far in your story.
It could be. But could is the operative word here. and what's really important for people to realize is that most scientific ideas are wrong. Most
Yes.
good scientific ideas are wrong.
Yeah.
I mean, I've had a great number of good ideas.
And some of the bad ones are right.
And so what I have talked about in the past, and I think, and I even wrote a book about string theory, and I think it's a very well-motivated idea, but I hate scientific hype. I hate hyping things more than they are, because it comes back and bites us in the butt. And so string theory was held up to be this amazing theory that was just going to do everything in a few years, and more people know about superstrings than know about superconductivity, but one actually exists. We don't know if superstrings exist. We don't even know if they're extra dimensions. Most people think, because the publicity was so effective, that we know there are extra dimensions in nature beyond the ones the four we know of, because in most string theory, it's a requirement, okay? But all of that is just ideas, and it's great for you and I as physicists to talk about it, and it's really important for people to spend their lives thinking about it. But it hasn't done anything yet. As my friend Frank Wilczek, who I was here when the Nobel Prize, said, string theory, and along with your former supervisor, David Krauss, string theory is very promising. And it keeps promising, and it keeps promising, and it keeps promising.
Okay, but we'll see. I mean, it might deliver one day, but I agree with you. There has been a hype, but that doesn't mean that it's wrong.
No, it's really well motivated, and it's incredibly interesting and quite exciting. But it hasn't. There are so many areas of science where we've done so much more in terms of explaining how the universe actually works, that I feel sad that a very sexy but speculative idea is more known by the members of the public than the really beautiful ideas that actually explain nature.
But you're not against it.
Oh, no. Well, some of my, as I like to say, it's true that
some of your best friends are string theorists.
Some of my best students, have become string theorists. Okay. I just wouldn't want my daughter to marry one. That's all.
Okay, so I shouldn't ask you about the multiverse and all of that. That's okay for you.
The string theory generally predicts a multiverse, but in fact, normal, everyday, four-dimensional physics predicts a much more well-motivated multiverse, in my opinion, which is inflation, this idea that the universe expanded very rapidly early on and caused basically most of the conditions in our universe that we now see. It's a beautiful idea, and I've written about it, but one of the things it generally predicts is that inflation is eternal, and universes basically come into existence when a small region of the universe sort of condenses out of inflation, like an ice crystal. And then that universe becomes a Big Bang. And then somewhere else, most of space is still expanding, and somewhere so far away that we'll never see it because it's moving away from us faster than light, another universe may come into existence. And in each of those universes, the laws of physics can be different because you can descend to a different vacuum. That is well motivated, and what I find particularly exciting, which brings us back to the beginning, in a way, is, and I've been working on gravitational waves of a different sort for 40 years or so, if we could measure a different kind of gravitational wave than what LIGO measures, and not even the ones that LISA measures, but maybe 50 or 60 years down the road, gravitational waves from the Big Bang itself, which was an incredibly cataclysmic event, we think produced gravitational waves of all frequencies. If we could measure those, we could actually come extremely close to proving that there are other universes. And I find that amazing when you can turn metaphysics into physics.
Okay, we have to conclude just in a moment. But I have to take this opportunity. I mean, we are sitting here now. A lot of people will talk to you afterwards here. So I would like to, if you could put the signature in this book. It's the physics of Star Trek. It's one of my...
If you tell me I wrote this when you were a kid, I'm going to hate it.
So I would be very happy if you could write something.
Okay, sure, absolutely.
Yeah. I wonder, are you planning to write a sequel to this, because there is this new series now?
Yes.
On television, and there is lots of new exciting physics there. I couldn't find an explanation for that in the book. So
okay.
I'm looking forward to.
Well, I have updated this book several times when new Star Trek series came along, but mostly because there was new science. But I'm happy to say there's nothing in this original that's wrong.
Okay.
But I'm even more happy to say that I guess I can say this. We're not on TV, are we? Yeah, we are. Okay.
Actually, I think we are.
Anyway,
it's a different channel.
There are negotiations underway for me to appear on the next series. So
oh wow. Okay. Thank you very much. Thank you.
Thank you.